Greetings from the Department of PCE. In this video, we'll be learning about TSPC dynamic logic. So far we have seen static, ratio as less, ratio less, and then we move towards switch logic, transmission gate and pass transistor, and then we move towards dynamic logic styles. So basic dynamic logic style, recharge and evaluation phase, all those we have seen, and domino, which will include both the transitions being possible, and NORA, uh, okay, no race condition, and then now we are into TSPC, that is true single. So why TSPC? So if you see a normal chip design, and if I'm designing a chip and I have allotted some power, uh, for example, ஒரு பர்டிகுலர் சிப்புக்கு இவ்வளோ பவர் நான் அலாட் பண்ணியிருக்கேன் அப்படின்னா அந்த அலாட் பண்ண பவரில் ஓவரால் பவர் கன்சம்ஷன் பார்க்கும்போது அதில் 50% ஆஃப் த பவர் வில் பி கன்சியூம்ட் ஃபார் கிளாக் ஜென்ரேஷன் அண்ட் கிளாக் டிஸ்ட்ரிபியூஷன். இந்த கிளாக் டிஸ்ட்ரிபியூஷனுக்கு நிறைய பவர் வந்து கன்சியூம் ஆகும். த ரீசன் இஸ், for example, when you go for two-phase clock, okay, clock bar ரெண்டு விதமா நீங்க கொடுக்கணும். நான் ஓவர்லாப்பிங்காகவும் இருக்கணும். நான் ஓவர்லாப்பிங் அப்படின்னா clock பாரும் it will not overlap. When it is in 0, clock bar will be in 1. So non overlappingaகவும் இருக்கணும், and it should be properly disseminated, properly distributed to all the nodes at appropriate times. Okay, so that has to be taken care. And whenever you use more number of phase, the wires will increase, that is interconnections will go on increasing. So lengthy interconnects as well as more number of interconnects will result in RLC, parasitic RLC. Okay, and each and every wire have its own associated capacitance. They are conductors, they will have its own capacitance. Okay, so these all will change the working of my circuit. So எப்போல்லாம் RLC உங்களுக்கு கூடுதோ அப்போல்லாம் உங்களுக்கு பெர்ஃபார்மன்ஸ் வந்து உங்களுக்கு கம்மியாகும். Unnecessary RLC combinations வரப்போ obviously your performance will get degraded. Okay, and the main problem is clock skew. For example, dynamic logic style we learned that when you cascade dynamic logic style, you face some problem. Transitionல கொஞ்சம் ப்ராப்ளம் இருக்குன்னு பார்த்தீங்க. இப்போ ஒரு 4 ஸ்டேஜ் இருக்குன்னா ஒவ்வொரு ஸ்டேஜுக்கும் நம்ம clock வந்து கொடுக்கணும். For all the stages, clock will not go at the same time. That is clock skew. And it will not be acting in the same way because clock is not distributed at the same time. For example, first stage 0 nanoseconds, second stage 4 nanoseconds, third stage 8 nanoseconds. It may differ. Okay, so this difference, they are because of thousands of reasons are there, but this difference will cause degradation in my working of the circuit. Okay, so இதெல்லாம் அவாய்ட் பண்றதுக்கு சிங்கிள் ஃபேஸ் கிளாக் வந்து நம்ம கொண்டு வரணும். ஒரே வேல்யூ கிளாக் மட்டும் யூஸ் பண்ணி அந்த சர்க்கியூட் வந்து ஒர்க் பண்ணணும். கிளாக் மட்டும் தான் இருக்கணும், கிளாக் பார் யூஸ் பண்ணக்கூடாது. Okay, so in the early 1970s and 1930s itself, the single phase clock design came into picture. Okay, these people, Yuan and Swenson, they tried designing a frequency divider circuit and a latch using this single phase clock system. Okay, so dynamic first we have seen, and then domino. So dynamic had some problem in offering both the transitions, and then we moved towards domino with the inverter at the output, buffer at the output, and then we had some race problem. So now we are moving towards NORA, okay, which will avoid the race conditions. Okay, so in the early 1970s itself, those two people which we have seen in the last slide, so they tried all these logic styles. Okay, so dynamic domino, some more logic styles are also there. C square MOS, that is clock to CMOS. So இதெல்லாம் நிறைய logic styles. They had their own advantages and disadvantages. So using all these they designed, and finally they came out with a single phase clocking to go for a latch design and a frequency divider. Okay, so there it started. So first we learned how to um, design a single phase positive latch. Okay, so this concept TSPC we are learning to as a dynamic logic style to design dynamic circuits. Okay, the very basic dynamic circuit will start now. Latch. Okay, so first we'll design a positive latch using single phase clocking. This is a positive latch. Okay, where single phase clock only clock is used. Okay, so now latch na உங்களுக்கு transparent mode, cold mode ரெண்டு இருக்கும். Okay, latch it will conduct the value or it will retain the value. So conduct பண்ணிச்சுனா transparent mode, hold பண்ணிச்சு retain பண்ணிச்சுனா அது வந்து hold mode. Okay, so now transparent mode la, so my clock will be 1, and what happens when my input is 0 and 1, we will see that. Okay, so now clock is equal to 1, it is in transparent mode. Okay, clock is equal to 1 and input is 0. Input 0 now PMOS on condition, NMOS is in off condition. Okay, so PMOS on அப்படினா என்ன ஆகும், VDD ல இருந்து path இருக்கு output, so pre-charge ஆகும் and output will be high. Okay, so this high output will turn off my PMOS in the second inverter. Okay, and NMOS will be in on condition. So இப்போ ரெண்டு NMOS மே onல இருக்கு, this NMOS is in on and this NMOS is in on condition, so you'll have path from output to ground. Okay, so you have a 0. Is my latch conducting? So I have a 0 here, I have a 0 uptime here. So it is in transparent mode when the clock is 1. What happens when input is 1? Input 1 are the NMOS on ஆகும், PMOS off condition ல இருக்கும். Okay, now if my PMOS is in off condition, obviously all the voltage at output will be drained to 0 and here my value 0 will be obtained. Again, this 0 will switch on a PMOS. This is in on condition and PMOS NMOS off condition. Okay, so PMOS on la irundhudu appadina pre-charge agum, so you have a high output 1. Okay, now is my latch conducting 1? Yes, it is conducting. What happens when your when your clock is 0? Okay, clock 0 irundhuduna it will retain the same state. Okay, it will not conduct but it will retain the same state based upon your input. Okay, so now we have learned what is positive latch. We'll go for negative latch also. Negative latch la உங்களுக்கு அப்படியே இது working வந்து similar தான், but what is different is here when clock is equal to 0, my latch will be in transparent mode, where when clock is equal to 1, it will act in the hold mode. That is 0 இருக்கும்போது it will conduct the value, inல இருந்து outக்கு value வந்து ஈஸியா propagate ஆகும். 1 இருக்கும்போது hold mode ல இருக்கும் அப்படின்னா உங்களோட value வந்து retain ஆகும். The state will be retained depending upon the input you feed. Okay, so now we have learned the very basic circuit latch, that is positive latch and negative latch. When you cascade both positive latch and negative latch, you obtain a register. Okay, latchக்கும் ரெஜிஸ்டருக்கும் என்ன வித்தியாசம் அப்படின்னா, latchங்கிறது level triggered. உங்களோட output வந்து it comes into that is your output will be obtained when you maintain the level 0 and 1. அது வந்து level triggered. Okay, edge triggered na your output will be obtained when you encounter a rising edge or a falling edge. Okay, rising edge na 0 to 1, falling edge na 1 to 0. So level triggered அப்படின்றது உங்களோட input level பொறுத்து output வந்து ரெஸ்பாண்ட் பண்ணும். edge triggered அப்படின்றது input உடைய edge condition, அதாவது உங்களோட rising edgeல இருக்கா இல்ல falling edge இருக்கா அந்த condition, at that instant of time your output will be, you can see the response. Okay, so when you cascade both positive and negative latch, you obtain a register. In upcoming slides you will see how to design a register, and you will see a D flip flop, that is D register, in the last slide. Okay, so here the advantage is clock is being reduced, clock load illa. Disadvantage என்ன அப்படின்னா number of transistors வந்து இன்னும் கொஞ்சம் ஜாஸ்தியா இருக்கு. Okay, so practically speaking, when you compare your static and dynamic latch, that is static and dynamic resistors, dynamic seems to have less number of transistors. Okay, in some cases, rare cases, you find number of transistors being increased. So this is the simplified version of true single phase clock latch. So you may wonder, why should I learn this simplified version? So simplified version ங்கிறது உங்களுக்கு வந்து வெறும் அந்த first inverter மட்டும் இருக்கும். Second வந்து you can implement based upon your design. Okay, you can implement either logic or you can go for a simple inverter again, or using if you want to form a negative and positive latch. Okay, and clock is being reduced. You can see in the diagram, clock இதுல வந்து feed பண்ணல. Okay, yeah? So this is a simplified true single phase clock latch. Okay, so only first inverter is retained, which is controlled by your clock. Okay, so இதுல என்ன main advantage na, transistors கம்மியாயிரும், clockக்கும் கம்மியாயிருச்சு. Okay, so this is one of the main plus point. Okay, so but இதுல ஒரு problem இருக்கு. என்ன problem அப்படின்னா, you will have same chart sharing problem over here. என்ன மாதிரி அப்படின்னா, so suppose ரெண்டுமே positive and negative latch கொடுத்துருக்காங்க. ரெண்டுமே when it is in transparent mode, when your input is 0 in case of positive latch, what happens? PMOS onல இருக்கும், NMOS offல இருக்கும், clock வந்து 1 transparent mode தான். ஓகே, ஸோ இப்போ PMOS வந்து ஆன்ல இருக்கு அப்படின்னா it will conduct and it will provide VDD at the output. Okay, so now I have VDD at the output, but what is at node A? This node A is the driving point of next transistor. இந்த நோட்ல என்ன இருக்கு அப்படின்னு பார்த்தீங்கன்னா VDD minus VTN தான் இருக்கு. Okay, so this transistor, okay, so it will not turn on the next NMOS. This nodal voltage, this will not turn on the next NMOS. Okay, this is a problem in case of positive latch. இதே negative latchல பார்த்தீங்கன்னா, so it requires a strong one to on. Okay, so that is not possible. So ரெண்டு ரீசன் சொல்லலாம். இந்த இடத்துல சார்ஜ் ஷேரிங் அதுவும் ஒரு ரீசன். இன்னொரு ரீசன் இந்த இடத்துல ஏன் VDD minus VTNனா, NMOS cannot pass a strong one. It can pass a strong 0, but cannot pass a strong 1, it cannot. Okay, so that is also two reasons are there, charge sharing as well as NMOS cannot pass a strong 1. And in case of negative latch, if you see, அதே மாதிரி transparent modeல negative latchல input வந்து ஹையா இருக்கும்போது PMOS off conditionல NMOS on conditionல இருக்கும், and clock is 0 obviously for a transparent mode of positive negative latch. Okay, so now what will be the condition? ரெண்டு NMOS on conditionல இருக்கு, the output will be drained to ground, that is you will have here it is supposed to be 0 but it is not 0. Okay, so PMOS cannot pass a strong 0, so here VTP will be there, this may not on the next transistor. Okay, so this is one of the disadvantage in case of your true single phase clock latch. Simplified version of the disadvantage. Okay, now this is a diagram of TSPC which shows that you can implement logic instead of that single PMOS and NMOS. So in that ஒரு single NMOS ஒரு single PMOS போட்டிங்கன்னா cascading of positive and negative latch னு சொல்லலாம். Okay, so இங்க வந்து you can implement logic also. Okay, so when similar working, when clock is low, your precharge happens. Okay, and this block will evaluate, this block will precharge. அதே மாதிரி இங்க clock வந்து ஹையா இருக்கும்போது இது வந்து pre discharge ஆகும். Okay, and this blocks will evaluate. Okay, so here 5 only is used, 5 bar is not used. Okay, and these also provide pipelined applications, pipeline structure கொடுக்கும். So exactly similar to NORA it will operate. So I told you we will learn basic D flip-flop or D register. Okay, rising edge triggered D flip-flop. So D flip-flop na romba simple. கொடுக்குற value அப்படியே வெளியில வரும். Okay, so rising edge trigger na your when it moves from 0 to 1, my output has to respond. Okay, so this is my D flip-flop using TSPC logic style. Now when clock is equal to 0, positive latch is in transparent mode. Okay, and this will pre-charge now. Okay, and what about the last inverter? So இது ரெண்டு தான் inverter. Okay, so in இப்போ clock 0 இருக்கிறப்போ D input உள்ள வரும், இது sample பண்ணி that is it will get the value of D. Okay, and this will pre-charge and the final inverter will be in hold mode. Okay, when clock is equal when clock is moving from 0 to 1, rising edge triggered இல்லையா, so rising edgeல போறப்போ இது வந்து evaluation phaseல வந்துரும். The inputs will be evaluated and the final inverter will be in transparent mode. Okay, so when it is moving from 0 to 1, clock வந்து 0 to 1 move ஆகும்போது உங்களோட input value D will be obtained as Q here. So the detailed explanation I have given in the next slide in form of theory, you can go through. So here when I see I require only 11 transistors, 3, 3, 3, 9 transistors, 9 plus 2 for inverter, 11 transistors. So similarly when you design D flip-flop using static that is static latch use பண்ணி design பண்ணும்போது 16 transistors வேணும், but now I require only 11 transistors. So this is how it works. When clock is equal to 0, sampling your input will happen, and the second inverter will go to pre-charge mode. Final inverter will be in hold mode. இதே வந்து clock வந்து 1 இருக்கும்போது, அதாவது ரைசிங் எட்ஜ் 0 to 1க்கு போகிறப்போ உங்களோட first inverter வந்து evaluate பண்ணும், input evaluate பண்ணும், and final inverter will conduct the value. Okay, that is output Q will be generated. So in an advantage வந்து you can have you can design both latch as well as logic. So latch, register இதெல்லாம் design பண்ணலாம். Apart from that, you can embed logic into the TSPC pipeline structure. As you have seen before the D flip-flop, I showed you NMOS logic and PMOS logic. So where you can embed your logic. Okay, logic design பண்ணலாம். Now all the common advantages that is applicable for basic dynamic logic cell will be applicable here also. And when you design properly, when you design with more clarity, you can have a glitch-free system in case of TSPC. And very importantly, no clock skew problem is available. Okay, the only disadvantage that you can tell is in at certain cases you will have more number of transistors, and when you go for a simplified TSPC, the strong 1, strong 0 problems is revisiting here. Okay, so that's all about your TSPC logic design style.